Corrosion of concrete. In addition to the external mechanical loads acting on concrete and which is allowed for in the design of the structures, concrete is also acted upon physically and chemically by environments. Concrete is said to be exposed to physical and chemical processes of weathering. The failure of concrete is related to the action of water on it. If concrete is not saturated with water systematically, its failure at temperatures below zero is precluded because the concrete will not suffer multiple freezing and thawings. No chemical corrosion of the fabricated stone will occur due to lime being washed out of it, or for instance, decay due to the formation of new chemical compounds which lack cementing properties, the formation of chemical compounds of a volume exceeding that of its components, etc. Besides water, concrete and stone are also acted upon by other weathering agents. The corrosion of concrete, or also known as corrosion of cement stone, is identical to the corrosion of rock and metal. That is, weathering of rock and rusting of metal. Corrosion of cement results in a loss of bond between newly formed particles of the cement and between the stone materials, that's aggregates of sand, crushed stone, gravel in concrete. Since any of the weathering cases leads to the destruction of concrete, none of them is tolerated. Leaching corrosion manifests itself only when the hydrocarbonate alkalinity of water is insufficient to ensure stable existence of lime in the cement stone, separating it by the following reaction. Uh, Calcium silicate plus water gives calcium, aqueous calcium silicate plus calcium hydroxide, and of other hydrated compounds. The rate of corrosion depends on the density of the concrete, flow velocity, water pressure. Soft water dissolves calcium hydroxide, resulting in the cement stone losing its strength. It is known that when concrete sets and hardens under optimum conditions, at the end of 90 days, up to 15% of free lime expressed as calcium hydroxide by mass is separated from the cement stone. In the presence of soft water near non dense concrete, conditions are created for the physical decay of concrete. Irrespective of the kind of Portland cement and its compressive strength, because the lime forming in the course of cement hydrolysis will be removed from the concrete by leaching due to its good solubility in water. The removal of 30% of lime due to its dissolution in water, also known as leaching, reduces the strength of concrete by more than 50%. Concrete undergoing this kind of weathering loses its other properties such as water impermeability, resistance to frost, salt resistance, abrasion resistance, deformability, etc. The density of concrete is of great importance to the rate of lime removal by dissolution. Concretes characterized by a high water tightness reliably serve in soft water because of considerable retardation of lime diffusion into the surrounding medium. Acid corrosion is provoked by any acid. The possible destruction of concrete in an aqueous medium is determined by the magnitude of the pH value. The final decay products of the cement stone constituents of concrete are silicic acid gel, calcium and aluminium salts of the acid attacking the cement stone, or when a weak acid is involved, the gel of aluminium hydroxide. The reaction goes in the following manner: calcium silicate aqueous plus water gives silica oxide plus calcium hydroxide. The corrosiveness of free acids is often but little responsible for the corrosion of concrete. However, these acids contribute to a dissolution of the carbonate film on the surface of concrete and prevent the possible formation of a carbonate film. The action of these acids creates favorable conditions for removal of lime by the process of leaching. Carbon dioxide corrosion resembles in many aspects to the acid and magnesia kinds of corrosion, because the action they produce may be reduced by the action of hydrogen ions on the cement, stone or concrete. When water contains magnesia salts such as magnesium chloride and magnesium sulfate, the hydrogen ions are formed due to the hydrolysis of these salts. The free carbon dioxide contained in natural water may not corrode concrete, or it may corrode it partly, or it may also act as a fully corrosive agent. What causes the various corrosive actions of free carbon dioxide? The action of water and carbon dioxide on carbonate rocks results in the formation of bicarbonates. The reaction goes in the following manner: calcium carbonate plus carbon dioxide plus water gives calcium bicarbonate. Similarly, magnesium carbonate plus carbon dioxide plus water gives magnesium bicarbonate. This process of turning insoluble carbonates into soluble bicarbonates develops in a definite time, and its reversibility can be expressed in the following manner. Calcium carbonate in solution when is added to carbon dioxide and water gives calcium bicarbonate, and on the other hand it may also proceed in another direction in a reversible manner, that it may convert into calcium carbonate solid, which may again return into the solution form. Only a fraction of carbon dioxide dissolved in the layers of water adjoining the solid carbonate reacts with the latter. The rates of forward and backward reactions become equal, that is, an ordinary chemical equilibrium comes in motion. The non-reacting fraction of free carbon dioxide is called as equilibrium carbon dioxide. The formation of calcium bicarbonate or dissolution of solid bicarbonate continues if the concentration of carbon dioxide increases or the concentration of calcium bicarbonate diminishes. A small amount of corrosive carbon dioxide in water is sufficient to provoke dissolution of the solid film of calcium carbonate on the surface of concrete. The surface of concrete sometimes gets strengthened by the corrosive carbon dioxide, provided this strengthening process proceeds till the entire corrosive carbon dioxide is bonded in accordance with the following reactions. That is, calcium hydroxide plus carbon dioxide is calcium carbonate plus water. Calcium hydroxide also reacts with calcium bicarbonate to give calcium carbonate and water. The destruction of concrete due to sulfate corrosion is associated with the formation of a stable complex compound under certain conditions. The reaction proceeds in the following manner: calcium sulfate plus tricalcium aluminate plus water gives calcium calcium sulfate plus water. The volume of this compound considerably exceeds the sum of the initial volumes of its constituents, and this causes failure of concrete resulting from the internal stresses originating in the cement. This compound, however, lacks stability with a change in the humidity of surroundings. Gypsum corrosion manifests itself in the formation of gypsum crystals. It may be provoked by an aqueous medium containing a large amount of sodium sulfate or potassium sulfate, and it causes destruction of concrete. Sulfate and gypsum corrosion may attack concrete structures simultaneously. Magnesia and sulfate magnesia corrosion also occurs. There are calcium ions in the pores and capillaries of concrete. Stable composition of the liquid phase filling the pores and capillaries of the cement ensures stability of the solid phase. This stability changes when water contains magnesia salts of definite concentrations. Then the following reactions proceed in hydrated Portland cements. Magnesium sulfate in a reversible reaction forms magnesium ions and sulfate ions. Complete dissolution of magnesium sulfate, that is formation of hydroxyl ions of hydrated cement lime and magnesium ions that diffuse into the cement of insoluble magnesium hydroxide having no cementing properties. Following reactions then occur. Magnesium ions plus hydroxyl ions forms magnesium hydroxide. Calcium hydroxide reacts with magnesium sulfate to form magnesium hydroxide and gives calcium ions plus sulfate ions. Calcium aluminate reacts with calcium ions and sulfate ions and water to form again a complex compound 3CaO, Al2O3, 3CaSO4, 31H2O and calcium hydroxide. Calcium ions and sulfate ions in a reversible manner react to form calcium sulfate and water. In addition to the destruction of concrete due to chemical weathering or various kinds of corrosions, failure of concrete as a result of the repeated combined attack of water and frost must also be taken into consideration. Such failure of concrete is due to the following reasons. Systematic thawing of the water frozen in the pores and capillaries. Thawing means water becomes in a liquid form from ice form. Repeated filling of the pores and capillaries with water and its freezing in concrete. The frozen water gradually expands in concrete on cooling. The formation of a complex salt in hardening cement containing alkalis, potassium oxide and sodium oxide, and amorphous silica of the stone materials proceeds with a considerable increase in its volume, resulting in concrete cracking. This corrosion may occur even at a slight content of silica.